All right, so what is electronegativity? So electronegativity is the measure of the pull an atom has on bonding electrons. So we talked about that pull between the electrons. If I'm more electronegative, so in our example, fluorine had a higher electronegativity of 4, where hydrogen was a 2.1. If I have a higher electronegativity, I pull more. So I have a higher pull on those bonded electrons. Okay, measure the pull on bonding electrons. So there's a trend. So the trend for electronegativity is that when I go from left to right across the period, it's going to increase. So it increases as I go from left to right. So the way we can think about this is metals are here, non-metals are here, right? Metals like to form cations, non-metals like to form anions. So if they like to be anions, they like to be more negative. So if I like to be more negative, I'm going to pull those electrons more. So that's why it increases. All right, when I go down a group, my electronegativity decreases. When I go down a group, the reason it decreases is because my size of my atom gets bigger. So if I'm a bigger atom and these electrons are between me, I don't really feel them. My nucleus doesn't feel them as much if I was smaller, because then I'd be closer to them. So the bigger my atom, it's a little harder for me to do the pulling. Okay? So if we say, if we look at the periodic table, I said it increases from left to right and decreases down. So that means that fluorine, because remember these guys are noble gases, fluorine would be the most electronegative and francium would be the least. So fluorine is going to be the most electronegative element and francium is going to be the least. So it can help you remember the trend. Now, the larger the difference in electronegativity, meaning I want to pull a lot, they don't want to pull at all, so I'm really strong. So if I'm fluorine and they're francium, the larger the electronegativity, the more polar the bond. Okay? And it's going to pull towards the negative end, towards the more electronegative atom. All right, so here's just the trend. So you can kind of see fluorine over here. These are the higher ones, and then as I go, my electronegativity decreases. Now there's some exceptions because the transition metals get funky, but if you know the trend for electronegativity, you're fine. You never actually have to know the exact numbers, just know the trend and you'll be okay there in being able to compare them and to use the electronegativity concept. Now, we talked about the difference. We said that if the difference was really high, like between these two, then it's going to be a really polar bond. So we can kind of categorize this difference based on how much of a difference there is between those two atoms. So say that the difference in electronegativity between the two atoms was 0. That meant that the two electrons, the two atoms, had the exact same electronegativity. So that it'd be like fluorine and fluorine. So if we're the exact same electronegativity, we're going to pull the same. So think about tug of war. I'm pulling, they're pulling, so does anything move? No, we have equal sharing. So whenever it's the exact same, we're going to call that a pure covalent bond. Because when it's a pure covalent bond, those electrons are right in the middle between me and the other atom. So pure covalent, we're right in the middle between the two. Now, what if the difference is low? There's a difference. When we're talking about pulling, I'm pulling a little bit. I'm pulling it a little bit to my side, but it's not a lot of pull. So if it's a little bit of a pull, but not a lot, we call this a non-polar covalent bond. Okay? So this is usually the case if my two elements, my two atoms, are different, but we're like right next to each other on the periodic table. So if I was looking at the periodic table and me and the other element were on the same area, we were like touching on the periodic table, then I would assume our electronegativity would be a very small difference. So we would be a non-polar covalent bond. Okay? What if it's a pretty good, not super high, but a pretty good difference. This is going to be our typical polar covalent. One of them is pulling, okay? So I'm here and I'm pulling, I'm fluorine, and I'm going to pull a lot, so those electrons are going to be right next to me. Now, let's think about this. What if I pull so much that the other one just lets go? If you've ever seen that in tug of war, I'm pulling, and then they just like fall over in the mud, and I have the rope and I win. So that would be ionic. So remember, ionic is a transfer. So say I want the electrons so much that I just take them. And so now I have the electrons and they don't. That's no longer a bond, that's me just taking them away. And so that's an ionic compound, and that's what happens when my electronegativity difference is a 2 or greater. So if it's a 2 or greater, this is when we have an ionic compound. And remember, we know if it's ionic if it's a metal and a non-metal. So in my example, if I was fluorine and it was francium, fluorine's a non-metal, francium's a metal, and we're the furthest apart on the periodic table, I can assume my difference is going to be really high, and I'm a metal and a non-metal, so it's ionic by definition. Okay? So we can actually look at where it kind of falls on a trend line. Here, so here we go, pure covalent, there's not a big difference. Getting a little bit of a difference, non-polar covalent, and then a big, they're shared, but they're unequally shared, polar covalent, and now they're being transferred, and this is ionic. All right? So we can see some examples. So here, this would be between 2 chlorines. So if it's the same atom, my electronegativity is going to be the same. So the difference in electronegativity would be 0, and that's a pure covalent bond. Here I have hydrogen and chlorine. I'm on the periodic table, but I'm not touching each other. So I know that my difference is going to be big enough because I'm not touching these two on the periodic table, but I know that it's 2 nonmetals, so it's got to be covalent because it's 2 nonmetals, and it's got to be polar covalent instead of nonpolar because I'm not touching on the periodic table. I'm far enough apart. And then here I've got sodium and chlorine. Sodium's on the opposite side, chlorine's on this side of the periodic table, so that means I'm going to be really separated. One's a metal, one's a non-metal, so all of that should tell me that my difference should be really high and ionic. So you can actually just think through what these numbers are, think through what the compounds are to guess what these would be without actually looking at the numbers. And so you're going to have to do something like that on the next problem coming up, is just to think about what do you think it would be based on its location on the periodic table. So this is just kind of a little bit of a summary table. So if it's a small difference, it's covalent or pure covalent, like Cl2. If it's a small difference, then polar covalent, and if it's a big difference, it's ionic. Okay? But you might be asking yourself, well, what if I want to talk about how polar that bond is in a more quantitative way? This is a very qualitative way. I'm just kind of categorizing it. But I'm not really exactly saying how strong that pull is. I'm kind of just putting it in a category. So if I want to talk about exactly how strong that pull is, then I can measure it quantitatively, and that's called a bond dipole. We're going to talk about that in the next lecture.